Hello, everyone. My name is Davis Sawyer. I'm very excited to welcome you to another tinyML talk. We have a really exciting topic today from Foroozan Karimzadeh, and we're about to get started. So let's go, and thanks everyone for joining us. So off the bat, a big thank you to our tinyML strategic partners, AZIP, Arduino, ARM, BrainChip, Edge Impulse, Efficient, Greenwaves, Gravity, Hymax, Imagimob, Infineon, Initera, Noda AI, NXP, Procter& and Gamble, HIM-IC, Pollen Technology, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST, Synaptics, Sentient, and TDK. Thank you for making tinyML possible. If you're new to tinyML, we're happy to let you know that there's a meetup group and a LinkedIn group that are very active. We have 17,000 and a half members in 49 groups in 41 countries. That's amazing. It's been a few years since I've read these numbers, and I think that's just remarkable. The tinyML community on LinkedIn has 4K members and 13,000 followers. The links are here. The QR codes are there. Also, this talk, as well as the slides, will be available on YouTube and on the tinyML website. Subscribe to our YouTube channel. There's 11,000 subscribers and 633 videos full of content, full of information, full of knowledge and how-tos, just like today's talk. So check it out. And this is new. There's a Tiny AI forum on PDM and anomaly detection for 2023. There'll be an interactive live webinar December 5th. It is free. It will be the same time as today, 8 a.m. Pacific time. Definitely check that out. There's also a call for the tinyML Research Symposium. There are papers now being requested. Use the QR code here to submit your tinyML innovation. And there's the summit. So for those who haven't been before, this is the premier flagship event in tinyML. You have to be there. It'll be April 23rd to 24th, 2024, where it always is in Burlingame at the Hyatt SFO. QR code is there. Lastly, 2023 Edge AI Technology Report. We're all in the business. We're all in the space. This is the guides to understanding the state of the art in hardware and software Edge AI. Check it out. Link is there, and a new one will be coming up next year. Couple reminders before we get started. The slides and the video from today will be available at tinyML forums and YouTube for tinyML. QR code is there. And one last request from me before you get to hear the speaker. If you have questions during the talk, please use the Q&A. The questions will be addressed at the end of the talk, so put them in there. I'll bring them up. They'll be sure to be addressed. We simply ask that you wait till the end of the talk to ask our speaker. So let's get started. Today we have Foroozan Karimzadeh. She is currently a postdoctoral fellow at Georgia Institute of Technology. She received her PhD degree at Electrical and Computer Engineering Department, Georgia Institute of Technology, under the supervision of Dr. Rauschwiri, in 2022. Her research interest mainly includes developing novel algorithms and hardware co-design for energy-efficient deep learning and large language models. She was selected as an MIT Rising Star in EECS 2023. Foroozan was awarded a prestigious Semiconductor Research Corporation SRC Graduate Fellowship, which is awarded in partnership with Texas Instruments. Also, she received the DAC Young Fellow Award at Design and Automation Conference 2022. Foroozan, we're very excited to have you today. Please take it away.
Thank you very much for the nice introduction, and I'm very glad to be here. So let's get started. Device, machines, and basically everything around us are getting smarter. AI augmentation will create 3.3 trillions of business value by 2025. For example, Gartner has forecasted that 80% of smartphones on the market will have on-device AI by 2025. So first, let's see, why do we want on-device intelligence? Data is exploding. It's been estimated that by 2025, the amount of data will double every time you wake up in the morning. So we need intelligence to analyze these data. First of all, I know most of you know what is edge devices and edge computing, but I'm just go over it quickly if anyone don't know about it. So what is the edge and edge devices? The edge is basically an endpoint where data is generated through some sort of devices or sensors, like your phone, smartwatch, and self-driving cars. It's been estimated that the number of connected edge devices will exceed 50 billion by 2025, which shows that intelligence is moving to the edge. Edge computing can enable real-time data analysis locally, which reduces the latency and increases the privacy of the data. It's also important where we need accurate and fast computation to generate results under strict latency constraint. For example, in self-driving cars, to detect a pedestrian right in spot. Artificial neural networks have shown remarkable performance in broad range of applications, from computer vision for detection tasks, in healthcare systems for data analysis and home monitoring of patients, and for natural language processing to help Siri works better. Deep neural networks, DNN in short, are a powerful form of artificial intelligence that can outperform human tasks at many tasks. DNNs are usually huge networks with millions of connections that are connected to each other, forming a very dense and complex architecture. Now that we know the benefits of AI at the edge, let's see what are the challenges that we face. While DNNs are powerful and provide high accuracy for complex tasks, they cannot be easily deployed on embedded mobile applications. First, because the models are large and often over-parameterized. It must be stored in a big memory, and accessing model parameters from memory, the external memory, consumes large amount of energy, and also they are computationally intensive, and obviously you don't want your watch gets too hot because of these computations. From the hardware perspective, also, edge devices are memory and power constrained, and power is the key, which ensures longer battery life. And again, you don't want your phone or your watch dies so fast. So these are some of the challenges which makes it hard to deploy large DNNs on resource-constrained mobile platforms. As I said, because the models are large, it must be stored in an external DRAM. The major issue is that accessing model parameters from an external DRAM consumes large amount of energy. For example, in 45 nanometer CMOS technology, accessing a 32-bit DRAM memory requires 3 orders of magnitude high energy than a 32-bit floating point add operation. So what are the solutions that we have to overcome these challenges and bring AI to the edge? We need to look at it from the algorithm perspective as well as hardware. Many of the algorithms that have been used to train DNNs on GPUs certainly cannot be applied on mobile platforms, and therefore we need more optimized and advanced algorithm. And also, we need efficient hardware design and heterogeneous computing to run demanding DNNs at low power. So here I developed a method called Twofold Sparsity, joint bit and network level sparse deep neural network for energy efficient RRAM-based computing memory. So in short, I designed a sparsity method which sparsify the network both in the bit level, where we have the data, we have the values in bit representation, and also in the network level when we completely sparse and make the values 0. So first, let's look at the motivations behind the twofold sparsity. The previous pruning methods, such as threshold-based pruning, blockwise pruning, and the weight sharing-based pruning, have gained very good performance by shrinking the network using sparsity and preserving the accuracy. However, these models and these methods are not designed to apply in the hardware and get the energy efficiency and memory efficiency, because for example, in random pruning, it adds another level of irregularity to the network, and in the hardware side, we need to have almost as 2 times as the sparse weight memory to save the addresses of the sparse weights and do the correct multiplications. So all in all, these methods are powerful from an algorithm perspective, but its mapping to hardware is inefficient, and they are not designed to address the real hardware bottlenecks. And they are required to store the locations of unpruned weight, which leads to a memory footprints as has 2 times than the original size of model. And this motivates me to propose the hardware-aware method to prune dense DNNs using LFSR-generated pseudo-random indices, which is used for the network-level sparsity. On the other hand, a traditional von Neumann architecture suffers from a latency and power dissipation caused by intra-chip data communication between PEs and memory. And therefore, CIM architecture has emerged to overcome these aforementioned problems by conducting the computation in the memory. In CIM, a memory itself serves as PE and memory. Here, in this slide, I'll go over the general idea of how computing memory architecture works. In this figure shows the CIM architecture exploiting resistance of memory cells, the memory cell retaining the weights, as you can see here, generates the current that is the result of bitwise multiplication. In particular, in CIM architecture, employing emerging memories such as RRAM have gained importance in achieving energy efficiency in computation for AI due to low latency and an appropriate on and off ratio. Most of the RRAM cells encode binary informations where the high resistance represents 0 and the lower resistance represents 1. When a word line voltage of 0 is applied, the bit cell is not turned on, and there is no energy dissipated in the process, except for the peripheral circuit. So current is 0. On the other hand, when a word line voltage of 1 is applied, a current is allowed to flow through the bit cell. So the takeaway from this slide is that having more zeros in the network as opposed to 1 reduces the total energy dissipated during the inference. Further, recent advances in RRAM technology has enabled multiple state per cell. In one particular implementation that has been done in our lab by my colleague shows that 4 levels, 2-bit per cell are possible with tight resistance distribution. This allows high memory density with 2-bit per cell, where each cell represents one of the 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. And here is the high-level architecture of the CIM voltage sensing multi-bit RCIM chip that is designed in our lab. So let me repeat this. In our work, 2-bit encoding is employed while securing sufficient resistant distance. The measured energy of a 2-bit weight in the in our method with using the test chip is shown in this figure, and which basically show that the energy required to multiplying to the 0, 0 is about 20 times less than multiplying to 1, 1. And this is the motivation behind the bit level sparsity of the twofold methods. In such a 2-bit cell encoding, it's desirable to have more 0, 0s and 0, 1 rather than 1, 0 and 1, 1. And this is, as I said, because of the energy requirement for the multiplication. So let's go over the methods of twofold sparsity, which is a joint bit and network level sparsity. It has 4 different steps. First, it's initialization. Second, training with regularization. Third, post-pruning, and fourth, retraining. Let me go over each of the steps one by one. So in the first step, as I said, we're using the LFSR pseudo-random sequence generating. LFSR is a very simple hardware that can generate a pseudo-random sequence based on this high-level architecture. And using these LFSR indexing, I created a mask of 0 and 1. So basically, the ones are the weights that I want to sparsify, and the zeros are the ones that I want to be kept. And using LFSR, I can easily control the percentage of sparsity. And also to start, I use the 8-bit pre-trained model. Second, I propose 2 regularization to add to the loss function. And the goal for these regularization is that the first one is regularize the network and in the network level. And the second one is for bit sparsity and sparsifying the network in bit level. So for the network level sparsity, the regularization is a norm of multiplying the weights to the masks, and basically by doing that, we force these weights to be 0, and the regularization is responsible to gradually reduce these specific numbers to 0. And then the second part of the loss function is using the regularization for bit sparsity. Let's look at an example. How the bit level sparsity is done first by using scaling. By scaling, I mean that I'm going to divide the weight matrix by a maximum absolute value of the weights. And computed WS. And then for quantization, I used a uniform based quantization based on the B, which is the bit precision of the network. And finally, after quantization, the weights are going to be between +1 and -1 with the quantized value. And then we're also going to divide it to the 2 to the power of bit precision -1. And then another contribution of my work, which is different from previous work, is that I use 2's complement. As you know, in the hardware, we use 2's complement format. because I'm doing bit level sparsity, the negative number in the twos format is different from using the normal format. And for the negative, by using this formula, I use the twos complement format to present the bit representation of the numbers. As an example, if we have the W of this vector, the S is going to be 2, which is the maximum value of W. And then I divide the weight by S and generate the WS, which is the vector between -1 and 1. And then for the quantized version, I quantize each weight to the, I'm using uniform quantization, so I quantized each weight to the integer values. And then as a WS in the binary representation, depends on the bit precision. We're gonna transform each number to its bit representation. And as I said, I use twos complement format to change it to the bit representation. This part is important because, like previous work, they just use normal format just to represent both negative and positive values. They are working in the algorithm side, but mapping it to hardware is insufficient. Especially my goal is to reduce the number of ones in the bit level. So that's why it's important to convert it to the twos complement format. And then here is the regularization for bit level sparsity. And as you can see, it's the norm 2 of quantized weight. The important point here is that, let me go back to each slide. And so each of these bits, right now, it's going to be a learnable parameters. So we're going to train the network, and by using the regularization in the bit level, we're trying to try to make these ones to zeros. And then the next step, because pruning and regularization, some of the weights might be very close to 0, but not exactly 0. I add a post-pruning step so that we make sure that all the weights that we wanted to be 0 is actually 0. And then in the last part, which is the retraining, I use the I'm gonna retrain the network another time for a couple of epochs, and use the mask weights to freeze the zeros in the network level, which is already sparsified, so we don't want we want them to be 0. And then we do a couple of rounds of retraining to make sure that we preserve the accuracy. And then here is the final weight sparse matrix that we're going to save, and then it's going to be used during the inference. Here I go over in the high level hardware for the inference and go over how the LFSR indexing is working. So this block shows the high level how the LFSR generates the pseudo random indices. The figure shows that the hardware resources and operations to solve a sparse, fully connected layer with M input neurons and N output neurons and SP as sparsity. For the hardware implementation of our proposed method, the LFSR is used to generate the index for the input to multiply to the corresponding weight values. in the sparse weight matrix. LFSR is, as I said, is the most commonly used topologies for implementing and generating pseudo-random bit sequence. It consists of an array of flip-flop with an initial state called input seed, followed by a linear feedback performed using several XOR gates, CI. LFSR can be mathematically described through an nth-order primitive polynomial and can generate the pseudo-random sequence with value between 1 to 2 to n minus 1. And n is the order of polynomial. And in order to keep the values between the number of the inputs, weights, and the neurons, we multiply the generated value to the length of the input neurons and select the most significant bits MSP here. And the goal is to avoid redundant clock cycle when the generated number is generated at the number of with the number of the neurons. This process generates the row indices, and we do the same for columns. And one thing that I need to highlight is that we use the same input seed and primitive polynomial once before training to create the mask, and we use the same one during the inference to make sure that we use the same, basically to for the addresses of the sparse weight matrix. And let's look at an example of how LFSR is working. And let's say we have an LFSR with primitive polynomial equal to x to 9 plus x to 4 plus 1, and the input seeds of 1, 1, 1, 0, 1, 0, 1, 1, 0. Also, the input neurons equal to 300. One of the generated output sequence from this LFSR can be 4, 6, 1. However, this value is greater than the number of input neurons, and one solution is to skip this number and take the next sequence, but this will cause a redundant clock cycle and decrease the performance. And to solve this issue, we multiply to the value of the input neurons, which is 300. In this example, and take the most significant bits. Here the MSV is equal to 270. In this way, we bring all the values to the range of the input neurons and prevent the redundant clock cycle. So the advantage of using LFSR is that LFSR can be easily implemented in the hardware. It preserves the rank of the generated connectivity matrix. Sorry for that. And real-time and automatic address generating using LFSR, and also there is no need to store addresses of sparse weight matrix, and this is actually the main goal of using the LFSR, which as opposed to the previous method that they have to save the addresses in the memory. By using LFSR, we do not need to save the addresses. Here is the results of the accuracy result of twofold sparsity. We used ResNet 20 and tested on CFR10 dataset. The accuracy of the network in different sparsity is shown in this figure. Accuracy before training and after post-training. And also here is the result for energy. And as you can see, the energy is decreasing as we increase the sparsity. And this is because we sparsified the network both in the network level and also in the bit level. In the bit level, we have way more zeros than the original values. So basically, the values are right now the values that are desirable for compute in memory, and also with network level sparsity. We could we increase the sparsity of the network, and using the LFSR, we could just simply find the right values for multiplications between the weights and the activations. And as you can see again in this table, that the energy required for 2-bit per cell of 00 is about 20 times less than multiplying to 11. And by using compute in memory, we can decrease the energy required for doing computing deep learning models during the inference on edge devices. Thank you very much for your attention, and I'm very happy to answer any questions.
Thank you so very much for this intriguing talk. This was an excellent presentation. So one question we have from the audience, and reminder to everyone, if you have questions, you can always message the speaker directly. But if you'd like it addressed live here today, please put it in the Q&A panel on Zoom. So one quick question, just give me a sec, Rizwan. So it says, can you please share the consulted reference sources for the twofold sparsity methods in today's session? So obviously you can share that if you can for us, but maybe speak to the consulted references if you can.
Yeah, definitely. I can share the paper related to this work, and maybe I can share it offline.
Excellent. Yeah, and as always, the presentations are shared with the tinyML forums. So if you go to tinyml.org, you will have the actual slides from today there, plus the YouTube videos will contain the talk. One more question, actually, I have two questions for you. This is a good one. So how can we control the sparsity? Since LFSR automatically generates random masks, there seems no room for controlling the sparsity rate.
So actually, we can control the sparsity, but LFSR generates basically pseudo-random sequence, and based on we have the length of the sequence, so we can actually select the 10%, first 10%, first 20% to generate the mask.
And that's preemptively, like before the experiments, you can actually generate the mask with that ratio.
Yeah, basically, so everything is defined before starting the training. So we know what is the input seed, what is the primitive polynomial, and for the LFSR, and then we generate the pseudo-random sequence and generate the mask and everything before training. As you remember, like I had the one step before starting the training with regularization. So in this step, which is the initialization, we're going to set everything, the percentage of sparsity, the network level sparsity, and the generated pseudo-random sequence.
Excellent. No, that's very clear. And this is great. I'm seeing more questions come in. Please, now's the time. If you have questions, now's your chance to ask. So next question from Harnish Patel. Can you please show the slide where it shows accuracy after applying the proposed sparsity and reduction in number of parameters? So if maybe it would help, but if you could go back to that slide where there's a table or a graph rather with the accuracy and proposed sparsity, and maybe speak to the intuition behind how accuracy degrades with sparsity.
Yeah, Dave, can you please help me, because I can just go forward if you can go.
Oh, I'm so sorry. Okay, give us a second. No,
Yeah.
you're right. Okay, please give us 1 second where we're gonna try to figure this out together.
Yeah,
I think we're good. Okay, awesome.
thank you. So Yes, so the sparsity we basically with the sparsity we remove some part of the network, right? So in at some point we can preserve the accuracy, but as we remove more and more weights, which means that we remove more information, so it's very obvious that we lose information and we lose the accuracy. But because I did the twofold sparsity during the training, it helps to maintain and preserve the accuracy. Like if you want to do just post sparsity or post quantization, you'll see that you'll get low accuracy compared to the original network. But because I've done it during training, and also I've done one round of retraining, I could preserve the accuracy um, compared to the original network.
Right. And this is the fun question. So it comes from Enginiyulu Venkatasan. So can we conclude that predictive power is with few neurons rather than the whole network? And I would preface the question by saying sparsity has been studied for some time in the AI space, and obviously biological brains carry some sparsity, but rather it seems that sparsity where it's needed and density where it's needed is the recipe for efficient intelligence. So the question again is, can we conclude that predictive power is with few neurons rather than the whole network? That's the question, but I'll let you answer it.
Um, so definitely we have this is a company, we need density, and we need like right now these, especially the new methods, the new algorithm, like large language models are huge, like billions of parameters. So we definitely
Trillions.
trillions, like recently, yes. So it's very hard to apply it on edge devices. So we definitely need to add some sort of sparsity to the network. But it comes with the cons of like maybe getting lower performance and accuracy. But at the same time, we can save the energy and memory of the system. So at the end of the day, it depends on what's
Yep.
the goal. Do we want to have lower energy doing computation, or do we want to get better accuracy and performance? And based on that, we can define the density and sparsity.
Absolutely. I think that's a great answer. So here's a follow-up question. It's anonymous. At the level of network, what type of layers can benefit from this technique to compensate sparsity? More specifically, I would like to get your opinion on recurrent neural networks.
Um, so this is it can apply for both fully connected layers and convolutional layers. I just implemented and tested on, like, for example, ResNet, AlexNet VGG. But I haven't tried it on recurrent neural network. But I believe it can apply because it's a fundamental method to do the bit level
Mhm.
sparsity, and you can definitely apply bit level sparsity to many other methods. So recently I tested this method, just the bit level part for generative AI and BERT model, for example, and we could get a very good performance for BERT models, and also for generative AI tasks. So it can definitely apply to any sort of real models, ML models.
Excellent. Yeah, I've heard recently that people are revisiting LSTMs and RNNs even in the wake of transformers and Gen AI models. That people are going back to these simpler models, compared to those models to see if they're effective. So, as we all know in tinyML, efficiency is key. So that was a great question. Here's a more practical one for us. So the question is, why are the weights scaled first before quantization?
Um, so the scaling is important. We're gonna so basically we want to scale the weight to the number of for example, to the integer. right? So first we gonna scale it to values between -1 and 1, and then scale this -1 and 1 and the rest to the integer, like for example -127 to 128. So we basically keep the scaling factor, and like, which is the maximum value of the weights, and then quantize the scaled value.
Cool, cool. So this is great. Everyone, these questions are why we're here. So please, if you have questions now, Q&A is the place to ask them. Next question for you is from Son. It's, I think one challenge when applying sparsity to CIM is how to deal with the mapping. Suppose in a 32 by 32 array, what will be done in your experiments if different columns have different non-zero locations? Although they have the same sparsity level, will the energy change in this case? Interesting question.
Can you repeat it? Suppose we have a
Yeah,
30.
sure. So imagine in an array you have different locations of the non-zeros.
Yes.
So say you have the same sparsity ratio, the same number of zeros, but they're in different locations. Does it change the energy consumption?
For the bit level sparsity, we're not gonna remove, so we still have the zeros in the
The mask,
value.
basically.
So for the bit level, no. So the mask is for which we controlled by
Ah,
LFSR.
I see. Okay.
So we're gonna do the same multiplication for values in CIM. So we're not gonna like removing the zeros in bit level sparsity, if I get the
Okay. Okay.
question right.
I think you do. And if the question's unanswered, please feel free to follow up. It sounds like regardless of where the zeros are, the
Yes,
number of zeros determines the energy consumption.
exactly.
Excellent, excellent. This is great. It's been a long time since I've talked about sparsity, so this is exciting. Can we regard the LSFR as an online generated lookup table? Good
Um,
question.
yes, that's a good interpretation of that. It's LFSR first, and yes, because
Thank you.
we can find the addresses on device on die. So basically we do it online.
Right. So it sounds like the answer is yes. You can find locations on die, and therefore it
Oh
kind of
yeah,
is like a generated lookup table in real time.
yeah, exactly. That's the goal of using
That's very cool.
LFSR, which we use, like we can use the same LFSR during inference and generates the values, the addresses.
Excellent. Excellent. That's it. That's very cool. So a couple more questions here. First one is, can you tell us pardon me, can you tell us what the exact accuracies are before and after training?
For resonant model, so it's what I got is about like 88 to 90.
Is that
Uh,
CFAR 10? Sorry for us.
yes.
Okay.
Yeah, for C14. I also tested
That's
on
typical.
internet data set, but I haven't bring the result here. But yeah, so because of the sparsity, we got a little bit lower accuracy compared to the original resonant model. But in terms of the energy and memory saving, we could save a lot. So it's so basically like a compromising like a little bit of accuracy to get better efficiency in the hardware.
Totally. Totally. Awesome. Life is about trade-offs. So we have one more question. It's anonymous. It says, not sure to be related, but how about activation sparsity? Any way to get rid of them during the training?
Um, so this is a good question. So I've seen some work on activation sparsity, but activations are the values that are generated based on the input and weights. The X times W transpose plus B generate calculate. We can create the we can compute the activations. But if we can sparsify activation somehow, we can actually get advantage using CIM,
Mm-hmm.
because in CIM, if we have zeros in the word lines, there is no currents flow through the cell, and there is no energy dissipated in the CIM architecture. So that would be one thing to explore, to see what happens if we sparsify the activations. But in this work, I mainly focused on the weights sparsity, because the weights are the values that are gonna be saved in the memory for inference.
That's it. Yeah. If you can skip the activations, then you skip a lot of resources. So, a follow-up question, I believe from a previous requester, Shikong. So, regarding the network sparsity, is it correct that in your hardware you will still save zero values in the array, but gate the memory access?
Yes. So we still not the network level sparsity, but for bit level sparsity, yes. So if we, like, for example, in the bit level representation, we actually changed some of the ones during the training to zeros, right? So we still have them, and we do it the whole number for the CIM. But for the network level sparsity, which is basically we sparsify the whole weights using the LFSR mask, we're not gonna save it in the memory. So
Got
we're
it.
gonna have one logic in the inference, which is the LFSR addressing, to make sure that we do the correct multiplications during inference.
Makes sense. Makes sense. Well, I think sorry for all the questions for us. Is Foroozan. It seems like you were very popular this talk. Thank you everyone for your engagement, for your enthusiasm, and for your interest. Thank you again for such interesting talk. Um, and thank you again to all the tinyML Street partners. These are the companies that make this a reality and a possibility. Thank you to our executive sponsors. Our executive sponsors are Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Thank you, Sentient, for making Edge AI a reality. And to our Platinum strategic partners, Sony, Atrios, deploying Vision AI at the edge at scale. And to the Gold strategic partners, ARM, build the future of tinyML on ARM. Edge Impulse, the leading development platform for Edge ML. To Infineon for driving decarbonization and digitalization together. Inotera for neuromorphic intelligence for the sensor edge. To Renesas, Renesas is enabling the next generation of AI-powered solutions that will revolutionize every industry sector. ST Microelectronics provides extensive solutions to make tiny machine learning easy. Synaptics is engineering exceptional experiences. And to the Silver strategic partners, which are AIZip, Arduino, BrainChip, Efficient, or Befficient, I think, sorry, Greenwaves, Gravity, Hymax, Imagimob, Noda, NXP, Procter & Gamble, Pimink, Pollen, Schneider, SensiML, Silicon Labs, and TDK. One quick reminder, because I think I forgot it. There was a survey sent out after the end of the talk. Please fill out the survey. It's very important to us. Thank you very much. And this now concludes our tinyML talk. So thank you so much for your time. Thank you for being here, and have a great day, everyone.